Let's see, how's this? All right, perfect. Okay, let's try that again. If I could bother you to silence your cell phones, please, we'd really appreciate it. Also, if you look around your seat, you might find a sheet of paper with a QR code on it that you can scan to enter a giveaway for an RTX 5090 signed by Jensen. So go ahead and take advantage of that. Without further ado, my name is Logan Hirsch. I'm a principal engineer at NVIDIA. I'm joined today by Natasha Anisimova, a senior solutions architect. We're going to be talking about how we can empower QA teams with multi-modal AI. This is a bug from an alpha build of CD Projekt Red's Cyberpunk 2077. It's interesting because it was detected by an AI QA assistant, but it's not a terribly important bug. It's easy to spot. It's not game-breaking. This bug needs to be tracked and it needs to be fixed, but it's not T0. It's not where you want your QA teams spending their valuable time. The reality is these bugs happen. All right, is that better? All right, thank you. The reality is these bugs happen, and they happen often. As games continue to grow in complexity and scale, we need advanced tools to help our QA teams meet these growing challenges. Tools that can identify these small issues, visually apparent bugs. Are we okay, AV team? All right. These small issues, lower priority visual bugs, thus allowing your QA team to concentrate on what matters most, on the meat of your game, what makes your game truly unique and truly cool. Yeah. Today we're going to look at how we can, at how games are growing along three main axes: size, detail, and systems. We're going to talk about how we can empower QA teams to meet this growing challenge with AI QA assistants and RAG tools. We're going to start by looking at the growth of games. Games are getting bigger. This is a small selection of some of the top-selling open-world RPGs from the last 2 decades. Here we see a consistent trend toward larger game worlds. This is great for players. They get a bigger sandbox to explore. However, every square kilometer added to the game is a square kilometer that needs thorough QA testing. As the size of game worlds has grown, so too has the stories that we're telling in these worlds. Here, we look at the time required to fully complete the main titles in the Far Cry series. Far Cry 6 takes nearly 3 times longer to fully complete than Far Cry 1. We consider full completion time here because every main story quest, side quest, collectible, and achievement needs to be meticulously QA tested. But even if we focus just on the main story, Far Cry 6 takes about twice as long to complete as Far Cry 1. Now, this extended gameplay is fantastic value for players. They get more story and more content packed into each game. However, it also means significantly more work for QA teams. Yep. Perhaps the best indicator of a game's size, or content, is its size on disk. Let's consider the Call of Duty franchise. Over the years, we've seen a significant increase in the disk space requirements for these games. While some of this growth can be attributed to higher resolution textures, the bulk of it is driven by an explosion of content. We're talking about more game modes, weapons, attachments, characters, customizations, skins, maps, and more. It's more really of everything. And it's not just the Call of Duty franchise. This is happening everywhere. Games have more assets, more dialogue, more locations, more quests. For players, this is great. This means a richer, more diverse game experience. But for QA teams, it means exponentially more work. It's more content to test, it's more potential issues to identify, and likely, it's more bugs to track. Now, this is just the picture at release. The QA journey doesn't end there. It's going to continue with every patch, every update, every DLC, and every expansion. Okay. Games today have extended lifespans. And this is most evident if we look at live service games. Here we consider League of Legends from Riot Games and Warframe from Digital Extremes. Both of these games have been around for over a decade, and they maintain large, loyal player bases through consistent content updates. Since its release, League of Legends has introduced a plethora of new content. We're talking 130 new champions, about 1,700 new skins, and many new game modes, some of which are practically standalone games unto themselves. Notably, all 40 champions that were in the game at launch are still playable in the game today. Sure, some of the original content has been updated and some of it's been reworked, but very little has been removed. This means QA teams are not only testing new content, but they need to ensure that the content in the game is not being broken with these new patches and updates. The same story holds true for Warframe. The game has expanded significantly, adding many new playable characters, 4 new open-world maps, and hundreds of new weapons. Yet the original content still remains. If you're a fan of either of these games, you know that I'm not doing them justice. There's a ton of new content that has been added to both these titles over the years that is not present in this slide. They've seen growth, balance patches, and tons of new content that we're not covering, and they've been enhanced with new technology and new art for players to enjoy. Now, these new content, balance patches, new technology, and new art all has to be tested by QA. This brings us to the second axis of game complexity, which is game detail. One of the best ways to appreciate the evolution of detail in games is by comparing an original game to its remaster. On the left, we have a screenshot from Valve's Half-Life 2, and on the right, the Half-Life 2 RTX remaster from Orbifold Studios made with RTX Remix. There's a lot to like in this remaster. We have improved lighting, higher resolution textures, significantly more detail in both models and the game world. This enhanced detail, which is enabled by new technology, gives players a more immersive gameplay experience, but it can also introduce new QA scenarios. If you consider the plant growing up the side of the building in the RTX remaster, that plant looks awesome, but it also introduces a new possible collision scenario. If we consider the complexity of the lighting here, we have reflections, we have refractions, we have improved shadow detail, and more, all that needs to be reviewed in QA. These higher fidelity, more detailed worlds give players richer, more immersive gameplay experiences. However, a more detailed world requires more detailed testing. The third axis of game growth is systems complexity. Game systems are becoming not only more numerous, but also increasingly complex. Let's examine the evolution of systems in the Civilization series. It's evident these games have become significantly more intricate over time. Once a system is introduced, players expect it in subsequent games. For instance, the tech tree from Civ 1 has made an appearance in every Civilization game, but enhanced diplomacy, culture, religion, city-states, and the civics tree have all found their way into Civ 7 in some form. And these systems do not live in isolation. They interact with each other to add strategic depth to the game. And as I said with previous titles, if you're a Civ fan, you know I'm not doing Civilization justice here. I'm not talking about natural disasters or great people. There's a ton of systems and content that is not present on this slide. But all those systems need thorough QA testing. Civ 7 is substantially more complicated to test than Civ 1. Looking ahead, we expect this is only going to expand. Generative AI and other advanced AI systems are going to enhance player experiences in games. If we look at Meaning Machine's upcoming title, Dead Meat, the game uses a local language model to generate NPC dialogue. This gives players the freedom to interrogate NPCs however they wish. Instead of following a fixed conversation tree, an AI generates responses, allowing each player to have a truly unique experience tailored just to them. However, this increased player freedom significantly complicates QA. With a traditional conversation tree, you can systematically test all possible paths through a conversation. But with a language model, player inputs are unconstrained, outputs can vary widely, it's significantly more work to test. You have to ensure that AI NPCs are going to stay on topic, in character, and respect guardrails. And these systems can be non-deterministic, which also increases the complexity of testing. Similarly, Krafton's upcoming title Inzoi employs AI-powered characters to drive a dynamic community sim. NPCs can change their behaviors based on their experiences throughout the day. This creates a more immersive and compelling simulation for players, but again, this added depth means more intensive work for QA teams. So in essence, while AI-driven systems are offering players more immersive experiences, give players unique experiences tailored specifically to their choices, and offer greater than ever player freedom, they also present new challenges that require more sophisticated and comprehensive testing. So we've looked at the 3 axes of game growth. We have size, which is the games are getting bigger and longer. They have more detail and longer tails of support. Detail, where technology is driving higher fidelity, more detailed worlds. And systems, games today have more systems, and the AI-powered games of tomorrow are going to be more complex to test. Now we arrive at what I believe is the fundamental challenge. A linear increase in game size, art detail, and systems causes a non-linear increase in your QA requirement. If you make your game twice as big, while also making your game significantly more detailed, your QA team has a dual challenge. They have more game world to test, but every square kilometer of your game world requires more detailed testing. You take on this QA burden not only during the development of the game, but also for any ongoing support that you plan post-release. So QA demand is growing. It's growing fast, and if you work with a QA team that's strapped for resources, you know this is a problem today, and if we don't do something, it's going to get worse tomorrow. I'm just talking about this, and I feel a little bit overwhelmed. So the question is, what can we do to bridge this gap? What can we do to empower AI or QA teams to meet this challenge? And we did spoil it a little bit with this session title. We think that AI QA assistants can help bridge this gap so that QA teams can meet the growing demand. And we think we can do it in two key ways. The first is with AI QA assistants that can detect common game bugs, specifically bugs that are visually apparent, require consistent testing, and are tedious for humans to detect. The second is with RAG tools that will facilitate analyzing game data and bug logs to facilitate meaningful analysis. I'm going to discuss AI QA assistants, and then I'll pass things on to Natasha, who will cover RAG tools. So let's see how an AI QA assistant lets us help identify visually apparent bugs in games. First, we need some kind of gameplay video to process for bugs. This can come from human play or an automated walkthrough of your game. Next, we process that video with a vision language model that detects visual bugs. We then deduplicate the detected bugs and produce a detailed report highlighting all identified issues. And finally, we take that report and ingest it into your bug tracking system. Let's take a look at what this looks like in practice. This is an automated walkthrough of an early alpha of Cyberpunk 2077. As with any game alpha, there are many bugs to consider here. The AI QA assistant finds a couple. I want to focus on 3 specifically to highlight the capabilities of the approach. But before I do that, let's watch that one more time, just so you have an opportunity to get a sense of what this looks like without the assistant.
What is that? Oh, no.
So the text under this video shows the description of the bug that was generated by the QA assistant. So here we have a couple NPCs that are walking in place. That's all happening very quickly, so I'm going to pause on this frame for a moment. This bounding box is output by the QA assistant, and it helps us quickly identify where the bug is. To identify this, the AI needs some understanding of video, right? This bug is not apparent in a still image. The problem is that the characters are not moving forward over time. It's a pathing problem, so it's one of the things we want to highlight here. But let's take a look at a more difficult example. Here, the NPC in the purple shirt walks over the dumpster. She steps up as the camera turns. This is a blink or you'll miss it bug, and I'm going to be honest with you guys, I didn't catch this bug the first time I watched the video. Let's think about what the AI has to be able to do to detect this bug. It has to recognize that the character walking over the dumpster is not an expected or normal behavior. It has to track the character as it's stepping up on the dumpster. And it has to do all of this in just a couple frames, despite some very rapid camera movement and some very strong motion blur. Let's look at one more example. Here, the AI is identifying that the character isn't dressed appropriately for this scene. So the QA assistant here needs to have a good understanding of the context of the game world, right? It needs to understand that in this environment, it doesn't make sense for the character to not be wearing a shirt. To complicate matters, this bug is only visible on the edge of the frame, and it's only visible for a couple frames. So I want to take a step back and think about what the manual effort required to detect these bugs is. First, you need to identify the bug. Some bugs are obvious, but some bugs occur in busy environments and are only visible for a couple frames. So this necessitates great diligence, and you may need to replay or repeat content repeatedly so you can catch everything. Then you have to provide a description of the bug. You also need to capture bug samples, and if the bug is subtle, you might also need to provide some annotations around the bug to highlight where the issue is. And finally, you need to add that bug to your bug tracking system. Now, individually, this might not seem like a lot of work for a single bug, but when you multiply this effort across a multitude of bugs, it quickly becomes a significant manual effort. The video we just showed comes from a very small portion of the Cyberpunk game world. If the entire world has a similar bug rate, we're potentially looking at hundreds of thousands of bugs to identify, describe, capture, and track. I would submit to you this is not where you want your QA team to spend their valuable time. Instead, we should approach these visually apparent bugs similarly to how we evaluate performance. For each new nightly game build, let's split your world into manageable chunks and conduct automated fly-throughs of each section. Capture videos and run them through automated bug detection. This can all run in parallel, so when your teams come into work in the morning, you'll have a comprehensive report that tracks bug improvements and regressions compared to previous builds. So this is an example of what that might look like, what you might be tracking over time at a very high level. Here, the latest build is addressing some clipping and floating issues, but there are some new broken mesh and animation issues to consider. Because you can run this on a nightly cadence, you can track the occurrence, the addition, or loss of bugs over time and link them with specific change lists. This systematic approach lets you efficiently monitor and evaluate the quality of your game with every iteration. It helps you spot regressions quickly and identify where you want to put more QA attention. If you identify maybe the city center has a very high rate of bugs, you can deploy your QA team to investigate that more thoroughly. To build this report, we need to complete two tasks. First, we have to be able to detect bugs, and second, we have to identify that multiple different detected bugs are in fact instances of the same bug in your game world. So these videos showcase two instances of the same bug captured in Cyberpunk 2077. The QA assistant first detects these bugs and then recognizes that they are instances of the same issue during the deduplication process. As a result, this would be added to your bug tracking system as a single bug with two example videos. In this way, we ensure that every reported bug is truly unique while also tracking each detected instance of every bug throughout your game. So let's talk about how this works. First, I want to define some terms from just 10,000 feet in the air. We're using large language models and vision language models to help with bug detection. You've probably heard of LLMs, or large language models. They've been making waves since the release of ChatGPT. Large language models take in text and output text. They're trained on trillions of tokens, and a token here is a word fragment, or a character. And they're trained in two high-level steps. First, they're pre-trained to perform some very sophisticated auto-completion. So given some context, predict what comes next. So given the context, Logan seems, we would hope that the LLM would output nice to give us the sentence, Logan seems nice. After this pre-training step, models go through supervised fine-tuning and reinforcement learning to train them to act as assistants. What's really cool about this is that after this training process, models exhibit some ability to reason. Vision language models, or VLMs, take all the goodness of LLMs and they apply it to the vision domain. So they take in images and text, and they output text. They're trained on billions of image and text pairs, and we really like them for bug detection for two reasons. The first is, because they can output natural language, they can give us descriptions of the bugs that they detect. But the second, and perhaps more importantly, is because these models are trained on real-world content, they have a fundamental understanding of physics and how the game world is supposed to function. And this helps them identify issues in games that other systems might struggle with. With that in mind, let's take a look at the bug detection flow. So we need to take some gameplay video that's been captured from human play or an automated fly-through that we want to check for bugs. The first step is to process that video and extract keyframes. Instead of analyzing every single frame, we filter down to a select few that collectively represent the entire motion sequence in the video. We extract keyframes here for two reasons. The first is efficiency. We just don't want to waste computational resources processing frames that are near identical. The second, and perhaps more importantly, is dynamic control. Keyframes give us the flexibility to manage how much video the model examines for bugs at a given moment. Vision language models have a limited context or input size. So let's consider a model that can process 20 frames simultaneously. If your game plays at 60 FPS, then we would have to process every third of a second of gameplay for bugs. But we might not need to do that, right? If you have a character who's standing idle in a room, not really moving, not doing much, or your player's kind of going through a menu like a crafting system, we might only need to extract one keyframe per second. There might not be a lot visually interesting happening. By the same token, if we have a boss battle with many players and there are a lot of particle effects going off and tons of cool animations, we might want to process every single frame of that fight so we can properly detect bugs. By using keyframes, we can sort of control how closely the model is watching the video for bugs. And by smartly selecting keyframes, we can ensure that this process is both efficient and thorough and adapts to the gameplay that we're evaluating. Once we have keyframes, we create chunks of sequential keyframes and pass them on to the VLM for bug detection. The VLM input is a keyframe chunk that includes the timestamps associated with each frame, so the model has an understanding of how time is passing, a description of the game, a description of the bugs that we're looking to detect, and a description of expected behaviors that are unique to the specific title. And I'll get back to that one a little bit more later. The model will then output a list of detected bugs along with localization information that we can use to build bounding boxes. This gives us a list of bugs that we detected in every chunk of the gameplay video, but some bugs are going to persist across multiple gameplay chunks. So if you imagine the whole time I've been presenting, let's imagine this podium was floating and we processed this video for bugs. We would have, let's say, 50 different instances of floating bugs, right? Because the podium's been floating in every chunk. We need some process to recognize that we don't have 50 different floating bugs. We have one floating bug that's been persisting across all chunks. So we pass the VLM output into the large language model, and we ask the LLM to help us deduplicate bugs. And the LLM will recognize that and consolidate that into a single bug for us. Now we can run deduplication on a single video, or we can run deduplication on multiple different videos, so we can deduplicate bugs across different areas of your game world. Deduplication gives us a structured bug report that can then be reviewed by a QA engineer, or it can be ingested into your bug tracking system. I want to go back now to VLM bug detection, where I talked about expected behaviors as a model input. If a QA assistant identifies a bug, it's really important that there really is a bug there. We don't want to spam you with false bug reports. The problem is that many games include systems that defy real-world logic or differ from other games. So take double jumping, for example. In most contexts, double jumping would be a bug. But maybe in your game, double jumping is an expected behavior. So to address this, we give the VLM a detailed description of the unique behaviors in your game that would typically be considered a bug, but are expected in your game. And this ensures the model has the context it needs to make accurate assessments. So as an example, this screenshot shows one of the bugs identified by the QA assistant in the video that I showed earlier. Here we see the same NPC model is duplicated multiple times. Generally, this would be a valid bug to report. But maybe this is an early alpha build of the game. We might have limited assets. We might have limited models. This might be expected. So we can instruct the VLM to expect some duplicated models due to asset limitations, and then the VLM will follow this guidance and avoid flagging this bug.
Okay.
In summary, our goal here is to address the drudgery of QA by automating the handling of bugs that are tedious to detect and track. QA assistants do not do what QA engineers cannot. They do what QA engineers should not. You want your QA team focused on the meat of your game, what makes your game uniquely cool and uniquely yours. And your QA team's plates are overflowing. You've got work critical issues and testing game mechanics and quest flow and UX and balance and difficulty and more. The bugs on this slide are a sample of some of the bugs found from just 25 seconds of game footage, and none of them are unique to this game. Players are not going to tell their friends, go buy this game, it doesn't have any clipping bugs. These need to be fixed. Players don't want to play a buggy game, but players will buy your game specifically for its unique mechanics, setting, and story. That is where you deploy your QA team. So we have a tool that helps us find all these tedious bugs. That's great. There's one problem. Now you found all your bugs. And that might sound like a joke, but if you've ever opened a Jira project that has tens or hundreds of thousands of bugs in it, you know it isn't. So now that we found all your bugs, I'll pass things on to Natasha, who will talk about what comes next.
I'm a little bit shorter. All right. Can you all hear me? Sounds good. All right. You have thousands upon thousands of bugs. Now what? So I'll be covering what a RAG assistant for bug investigations might look like, how RAG systems work, and how you can get started today. So searching for visual bugs. Let's say I'm starting off my day. I'm gonna try to focus on the level that has the most bugs in my game. And as we can see here, level 47 has the most bugs.
Right.
And I wanna go ahead and say, all right, what are the top 5 bugs in level 47? We can see that there are 5 categories here: clipping, floating, T-pose, NPC behavior, and UI issues. Clipping by far has the largest amount of bugs, so I'm going to dive further into that. Which assets are featured in these clipping bugs on level 47? Maybe that can give me a summary of maybe it's only one particular asset that's causing most of these. So in this case, we see that 78 out of the 120 clipping bug descriptions for bugs in level 47 mention car assets. So from here, I want to go ahead and provide me a list of bug IDs on level 47 that relate to car clipping issues. So it'll go ahead and spit those out for me. I'll take a look at the first one. Maybe just solving that first one means that will help me or provide me a solution to solve the rest of these. Another way that you could go about chatting with your retrieval augmented generation is searching for priority 0 bugs. So let's say I've created a game, it's called Black Star, and I want to know what the P0 bugs on this project title are. So here we can see that there are 4 P0 bugs tracked. It gives me the bug ID and the description, and one of them has to do with a black screen when entering on level 3 on desktop. So let's dig into this further. Maybe this has been solved on a different game title. Maybe it's been solved on my previous game title. So if I have my old game database or old bug database loaded in with my current bug database, I could go ahead and search on both of them. And I can see what black screen bugs have been resolved on PC. So here we can see that it's brought me back 2 different bugs that have been resolved in the past. And I'm going to dive deeper into one of them and try and see what are the commonalities between the current issue that I'm trying to solve and this one that's been solved in the past. So here we can see that both these bugs have a crash log that lists the following errors. And I want to know, what was the solution for the old bug that was resolved? And we can see here that it was resolved by updating graphics driver. So in best case scenario, this would provide a fix to your issue. In worst case scenario, it gives you a starting point. Maybe it even gives you the name of the engineer who has solved this issue in the past and provides you some resources on where to get started on searching in your current game engine.
Good.
So retrieval augmented generation. I'm going to dive deeper into that. So what is RAG? I'll be referring to retrieval augmented generation as RAG from now on. It's just a little bit simpler. RAG uses information provided by the user input query to search a database consisting of domain-specific data, and then sends this additional data to the model that enables it to use new information to respond to the original query user. So what does a RAG need? It needs a data set. That could be, your current bug database. It could be an old bug database. It could be both. It needs an LLM. Which one? That's your choice. And you need a machine to run it. You could run it locally depending on how much memory you have available. So why use retrieval augmented generation? LLMs have fundamentally changed how we interact with technology, providing powerful tools for a variety of tasks. However, there's a caveat. When it comes to enterprise-level applications, the challenge, accuracy. Typically with LLMs, you are able to prompt it and get a response, but that response won't have proprietary knowledge, like games that haven't been released yet. You also run the risk of having outdated information. This can look like trying to get information about a current build that is in the pipeline, but the LLM has only been trained on a build that's available for public consumption. So how do we reconcile the power of LLMs with these challenges. The key is connection. Linking LLMs to live enterprise data sources to ensure the information they generate is both accurate and current. So RAG provides the ability to connect these LLMs to data sources, which as an example can be your bug database. It allows you to put all the smarts and language capabilities of LLMs in front of your most valued data. That could be your bug database. And have a natural UI interact with the company's internal data. This slide shows a high-level view of what the RAG workflow looks like. The diagram on the right shows your data embedded into a vector database, which can then quickly be searched. At runtime, the prompt comes from the user via a data framework for building applications based on LLMs. The prompt is going to trigger a search in the vector database. The information retrieved from the vector database is going to be connected to that prompt and passed to the model. Source content is provided to the LLM so that it can understand, digest, and formulate an answer based on relevant information pertinent to you. So what are vector databases and why are they used in RAG solutions? A vector database is a type of database that stores and organizes information using vectors, which at a high level are simply mathematical representations. Vector databases allow for a quick, accurate retrieval of relevant information based on similarity metrics. For example, if you're searching for similar documents, bugs, or build logs, the database can efficiently locate items with vectors that closely match the query vector, so your prompt. This capability enhances the generation process by providing a foundation of related data for the system to draw upon, improving the quality and relevance of the generated output. With RAG, we use the LLM to provide an answer using the RAG's knowledge base. As we delve into the world of retrieval augmented generation, or RAG, one fact becomes crystal clear. The quality of text embeddings is pivotal. Let's break down why this is crucial. Imagine a user asking, what build version of the game has the most bugs? This is where the rubber meets the road with RAG applications. We're not just looking for any answer, we're looking for the right one. On the screen, we see two pathways. One leads to a response. Windows 10 is the most stable Windows build, and it's based on low-quality embeddings. These are the basic blocks of information that are pieced together to form a response. However, if the embeddings are low quality, like the ones listed here under build, operating system, and source, the answer might be off. It's a shot in the dark. Now let's shift to the high-quality pathway that you can see below, powered by NVIDIA's retrieval QA embedding model. When we ask the same question here, we get build version 0.15 has the highest bug count due to missing assets. This answer doesn't just pop out of thin air. It's informed by high-quality embeddings, detailed, nuanced, and specific, considering game build, operating system, assets, device, and source. This isn't just about getting more data, it's about getting the right data. High-quality embeddings mean that the system understands the context better, the game, the assets, and crucial details that ensure the response is not only accurate, but also relevant. The takeaway, quality matters. In RAG applications, high-quality embeddings lead to answers you can trust, powered by NVIDIA's commitment to precision and reliability in AI. let's not settle for less when it comes to important questions. With NVIDIA's Retrieval QA embedding model, we have the tools to ensure that quality information is always at your fingertips. Here's a list of LLMs that you could potentially use. I'm sure I've missed some of them. I would encourage you to do your own research and pick the LLM that best suits your needs. Keep in mind that every model is going to behave in a different way. You can go through the process of setting a framework for test validation. Also, when you use these LLMs, there are many parameters that you can set to use to influence the response of your models. One of the most common examples you will see is temperature. Bringing the temperature closer to 0 means more consistent answers. Lower temperature will get you a more predictable answer where the model selects the closest token. And this is good for things like bug IDs, build logs, crash logs. You can think of it as a token, as a word, but it doesn't always have to be that. The higher the temperature, the more creative the response will be. An example where you could use this is maybe for creative writing or emails. And going back to how you can leverage RAG in game studios, RAG can point at your previous game's bugs. Bug tickets can have a link to a solution where issues were closed, providing faster ideation on getting those solutions. You could get insights on previous investigations done with similar bugs. Code retrieval and build logs as well. And if it's embedded on your current bugs, you can find similar issues in your bug databases that maybe you'll be able to see what they have in common. You can pull insights into your highest priority bugs, find problematic locations or assets in the game, devices, and particularly with devices, let's say you're enabling cross-platform and also mobile. If you're seeing that one of those devices is causing the majority, like 50% of your bugs, maybe that's something that you take to the engineering team and say like, hey, this is gonna take a lot more effort to get working on this particular system and it's 10 years old. Do we really wanna support it? And also the detection of rendering-based bugs on video data. That's another thing you could pass in. So you're probably at this point wondering, how do I set this up? There are many different RAG architectures out there, but I'm going to be covering one of them called Multi-Modal AI Virtual Assistant. You can find Multi-Modal AI Virtual Assistant repo for free on GitHub. If you guys want, you can scan the QR code. I'll also have it up later. I'll go through some of the steps that you need to get started. One of the first things that you'll see in the README is that you'll have to download AI Workbench, where it'll go through some steps to set up containers. You could use Docker or Podman, whatever your preference is. It'll go through setting up your API keys and also building the environment. So let me go over what NVIDIA AI Workbench actually is. NVIDIA AI Workbench is a development environment manager that provides a single pane of glass to develop, customize, and prototype AI applications on and across self-hosted GPU systems, from laptops to servers. With AI Workbench, developers can easily pull code and models from GitHub, NGC, and Hugging Face. They can set up a development environment and container of their choice and use frameworks, whether open source or production grade, available with NVIDIA AI Enterprise. These AI resources can easily be set up and streamlined with AI Workbench, after which developers can create, collaborate, and deploy their AI projects on a compute infrastructure of their choice. They can start locally on a laptop or on a workstation and scale out to a data center or cloud. AI Workbench also supports several major operating systems, including Windows, Ubuntu, and macOS, making it easy to migrate and reproduce projects across various environments. Let's double-click on AI Workbench. So you can pull this project down to a laptop, or you can choose to run things locally on a workstation, where you have enough memory to run the LLM locally. So running an embedding model locally to store documents in a private vector database, you could also use models like Llama 70B or Mistral 7B in the cloud via NVIDIA inference endpoints. And you can see here that there are a variety of ways that you could use laptop versus workstation. On workstation, you could potentially run an LLM locally. AI Workbench has an interface where you can easily set up your API keys, build and start your environment before opening the chat with RAG, where you can upload your data set and get cracking. So game developers need portability to create, customize, collaborate, and scale with ease and efficiency. However, significant effort and technical skills may be required, especially when the source and target environments are different. AI Workbench removes portability challenges and makes it easy to move projects like RAG to the best platform for cost, speed, and scale. Whether you want to run models in local or remote containers, or if you want to use public cloud APIs or private cloud microservices. Workbench projects allow a single unified developer experience, and capabilities include GPU hardware setup, endpoint handling such as credentials and secrets, development environment configurations including environment variables, data, and model or location changes, context and project management such as versioning. Developers have the flexibility and compute resources to run these experiments locally as well as on the cloud. And as you can see, AI Workbench can be used to manage interactive project workflows across the enterprise development environment, from experimentation to prototyping to proof of concept. So if you're getting started with the latest in generative AI for game development, you could be using it for QA assistance, for chat and retrieval of bugs for QA, finding similar bugs to help provide faster solutions, or perhaps even using the same reproduction steps for that other bug. Find potential solutions as well as pull trends and insights. So kind of like the device that I mentioned earlier, if it's a device that's 10 years old and causing 50% of your bugs, maybe you don't want to support it anymore. There's also another use case here, lore retrieval, where you can chat and retrieve lore. So let's say your game has 20 years of history behind it, and you're new. You don't have that history. You don't have time to read through hundreds of pages. You could use it to build upon storylines that already exist in the game. So let's say you want to marry off two characters, but you don't actually know if they're related in the past. This could be a good way to check that. And you can quickly locate specific information. So here's some links to get you guys started. NVIDIA.com/workbench. That's where you can find NVIDIA or Workbench. Also, the QR code is for the Multi-Modal virtual assistant. I'll give you guys a second. I'll have it up at the end too. So as you heard from Logan on VLM, we want to hear your pain points. What problems are you trying to solve? How can we make this better? Please come up and talk to us after the talk. And again, thank you again, with multimodal virtual AI assistant, you can try this today with your own data. And thank you for everyone that came to listen to this talk, as well as to the team that made this possible.
Thank you. No.
Oh, we have a microphone. If anybody wants to ask questions, please come up.
Right.
Hello, I have one, or
Hello.
maybe two. Keyframe selection. Is it automatized process, or it is something you need to, do manually? You said that it depends on the actual content you are going to process, or the, specific bugs you want to find. How
Yeah.
it is selected?
Yeah, so that's a good question. So keyframe selection is fully automated. What it allows us to do is to control how closely the model is watching the video, but that's fully automated. So essentially, you have some control over how you tune keyframe selection, how visually distinct each frame should be. But once you've selected that, it's fire and forget. You just say, go through, select all visually distinct keyframes we should process, and then those are selected. Now, if you find in your particular game, you think, well, we would like to watch the video more closely, we'd like to make that compute trade-off, then you can say, let's select frames that are less visually distinct, and then you'll gather more keyframes to evaluate.
Okay, but this is not automatically adopted, for example, that few, minutes of the video is on this rate, then on the another rate of the selection process.
Right, yeah, you're basically going to use the same keyframe selection threshold for the video you process.
And I have a second question, just VLMs. Do you have any, information? What are the best VLMs for given, tasks, basing on your experience on simulations?
So for bug detection in particular, this is still kind of early stages. We're not ready to release anything yet, but we want to share a lot more details in the future once we get close to that point.
Okay, but for now you are using public solutions, or this is something which you are building?
We're building a bug foundation model. Yeah.
Okay, thanks. Thank you.
I got kind of a similar question. So you mentioned the VLMs, but your examples were all about, like real-world-esque 3D environments, and that these models, have been trained off of like real world, so they have an understanding of physics. Well, what about for games that are primarily 2D and GUI driven and stylized? Are there any VLMs that you know of in the works that will handle those types of scenarios?
Yeah, so we are training the models on synthetic data as well, and in addition to that, data that we've licensed from partners. So our objective is to be able to handle varied art styles, 2D games, pixel art, you name it, with the goal to be to target those bugs that are really not unique to a particular game, but bugs that are prevalent in all games, right? Floating, clipping, T-pose, animation issues.
Hi. One of the big issues we kind of hear a lot about AI is there's their tendency to hallucinate data, especially when they don't have enough data to give you an answer. They'll make something up rather than saying, I don't know. Is that, and this is especially with the RAG issue, do you have guardrails in place against that, or is that mostly down to the choice of LLM?
Does this mic work?
Yes.
Okay. So RAG helps address hallucinations as well as lowering the temperature. So the higher the temperature, the more creative the response, or the further the token is. So the lower the temperature is where you're pulling the closest token into your database or from your database that matches the query that was passed to the model. With a lower temperature, LLMs will be guaranteed to select the most likely next token for each generation. So this will decrease the LLM's creativity in addition to decreasing hallucinations. So that's kind of the goal there. Logan, do you have anything to add?
Yeah, I would say one of the benefits of RAG is the additional context. helps the model draw from that, and it significantly decreases the odds of hallucination there. On the VLM bug detection side for hallucinating bugs, as we mentioned, we're very concerned about making sure that we're not spamming people with false positives. One technique we use to approach that is kind of have a honeypot bug for no bugs, so that there's still an opportunity to output something when nothing is found, and that helps significantly.
Thank you.
Hello. Oh, the last person was quite tall. Okay. Thank you for the talk. It was quite interesting. I just wanted to ask, so predominantly, maybe for my company, we would want to use this for optimization of testing, right? So if we had 1,000 characters that were unique and bespoke, and we wanted to do a visual update or some type of update to all characters, we'd want a quick way to do it. In your case, you require a video. So would you be requiring the QA tester to record a video of all 1,000 characters to determine this, or?
Yeah, so if the bug that you're looking for does not require video, then you could pass in a single image kind of as a single keyframe for evaluation. Okay. The benefit of processing video is that it helps us detect a wide range of bugs that you can't detect from a still image, right? An example would be if you see a car in the air, maybe it's a floating bug, maybe that car hit a bump, right, and is in the air momentarily. Maybe it collided with another car and that caused it to go in the air. So that's why we want to process video, so we have that understanding and can detect that range of bugs. But if the bugs you're looking for are visible in a still image, you can pass in the still image for evaluation.
I see. So but if the assets needed to be checked inside a battle-esque type thing where we need to check it inside the mode?
Yeah, I mean it's to be maximally robust, right? You want to test as close as you can to the real gameplay.
Okay.
Yeah, but however, I would say the good or way to think of it is how would you have your QA tester evaluate it? And that's probably a good way to think about it with the VLM, right? If you can watch the video and see the bug, then that's probably a good starting point.
Okay. Thank you.
Yeah.
Yeah. So, yeah, I gotta say, this section of this session was pretty helpful, especially after coming out of Tuesday's NVIDIA, which would discuss the various uses AI was going to be incorporated to game development as tools, and one of them is QA testing, to the point where one of those images in here was used back there. One point that I noticed and was very curious about more is the developer's ability to change how the AI would detect bugs to where the AI would not detect double jumping as a bug. It would not detect maybe a temporary assets or different configurations as bugs. So I'm wondering, how exactly does that play out in practice, especially considering especially for games with more unconventional features that would be considered as traditional bugs in other cases?
Yeah, so just to make sure I'm understanding correctly, you're saying you have a game that has a very unique mechanic, right?
Yeah.
It's very distinct to that game. How do we make sure we're not flagging that as a bug?
Yeah, pretty much.
Yeah. So it's a great question. There are kind of two areas where you can approach that. The first is to update the VLM prompt with that description of the behavior and the expected outcome. And that works pretty well. We're very focused on making these models instructable so that they can follow that instruction and respect it. And we're making sure we provide examples in training of expected bugs. The other option, if you know that bug falls into a certain class, maybe you haven't put textures into your game yet, right? It's just all blocked out, but you still want to test for other issues in the game. You can just say, I don't want to look at any texture issue bugs. I'm just going to ignore that entire bug class. And then we can just drop all those bugs as they come out of the system. And we can tell the VLM not to output them, but as a fail-safe at the end, we can also just say, drop them all, and then we're guaranteed not to have those get reported.
So for features, it's basically a prompt and several bits of data to show if that is an intended feature.
Yeah, we provide a text description of it essentially.
And images and video for data to prove.
Yeah, right now we're focused primarily on text as a description. Yeah.
Yeah, thank you.
Thanks.
kind of got two questions now based on that one response. But my first is, you mentioned synthetic testing, I think, for being able to maybe find a bug in a specific art style. So, I mean, I think that's how you described it, is like if there's a specific art style for a project that, you're trying to hunt down, you have a way of looking for a synthetic problem. Do you have does NVIDIA employ like a laundry list of various art styles to try to find bugs in, or is it just maybe like a handful as sort of beta testing?
Yeah, sorry. So to clarify what I was talking about there, we're using synthetic data to help train models, and synthetic data is a very complicated subject. It's probably worth its own separate talk. Maybe I can chat with you later, because I just got the 5-minute signal, and we can talk about synthetic data for till the cows come home. What was your other question? I want to make sure we have time for that.
Never mind. Thank you.
Oh, sorry.
I hope this one's short, if you're okay with that.
Yeah.
Thank you for the talk again. I just wanted to see what all the bugs that we've been looking at have been purely visual. I was wondering, have you guys looked into doing bugs that aren't visual based at all? Maybe like the player is able to do things that they shouldn't be able to do, things of that nature.
Yeah, we're certainly thinking about that.
Okay.
Yeah.
Thank you.
I'm assuming that the footage you showed of, for example, Cyberpunk, this is an example of this process wasn't actually used during Cyberpunk development.
No.
With NVIDIA's contacts with various game dev studios, are you aware at all of any studios that are implementing these kind of techniques currently or plan in future projects?
So this is very early right now, but if this is of interest to you, then let's talk. All right, I think we're low on time here, so thank you everyone for coming. If you have more questions, Natasha and I will stick around. We're happy to chat.